please welcome Kerst. Kerst is going to give a talk on Lunar In-Situ resource beneficiation. Is that how you?
Beneficiation. It's
beneficiation. Is
one of
that
those.
I'm not even sure what that word means. So I'm embarrassed to ask that. So could you explain what that means too?
No worries. I mean, beneficiation is kind of a mining term. It's basically extracting the valuable ore or metals from a specific type of mineral. So whereas in mining, you can have like the extraction side of things, which is using the big haul trucks and whatnot. And blasting, that's one side of a mine operation. And then you have the mineral processing side, which includes flotation. It includes stuff like other types of metallurgy, and that is basically the beneficiation process.
Okay, all right. Well, I'll hand it off to you now.
All right, well, hello, and thank you for all coming to my presentation on Lunar In-Situ resource beneficiation and the system of technologies that can potentially make it a reality. If you are here for the talk from Elon Musk and Jeff Bezos, it's a few doors down the hall. If you are here for me, then let me begin with an introduction. First, who even am I? My name is Kerst J.H. Kingsbury, and I'm a senior at the University of Arizona. I am pursuing a Bachelor of Science in Mining Engineering with a focus in mineral processing and a minor in planetary sciences. I'm also the Vice President of the U of A's student chapter for the Society of Mining, Metallurgy, and Exploration, or SME as it is better known in the mining industry. I'm also representing the Mining and Geological Engineering Department of the University of Arizona, along with being an internationally renowned, within the mining industry. We're utilizing and joining the strong space sciences foundation at the rest of the university in the greater Tucson area. Within our department, we have the Mine Intelligence Research Group, of which Dr. Tenorio, which is also right there, who we presented just an hour ago, another presentation, and myself along. Through MIRG, we are dedicated to research and development of world-class technical solutions and optimization through the entire life of mine. So here we get to the conceptual breakdown of just what I'm talking about. The utilization of key in-situ resources such as water ice and regolith materials found in the surface and near subsurface of the moon is fundamental to establishing a sustainable and permanent human presence there. These resources are principally found in permanently shadowed craters, especially near the South Pole. Developing new beneficiation technologies and techniques for these resources that differ from contemporary terrestrial approaches is an imperative. The new beneficiation technique I propose assumes an extraction technique of collecting both water ice and regolith without discretion over a wide surface area and shallow depth, which would be between 1 to 5 meters approximately due to the accumulation tendencies of water ice. The initial processing step, which is reducing the grain size, may utilize contemporary crushing machines, but should primarily consist of a focused electromagnetic pulse to aggregate both the water ice and the siliceous regolith. The eventual fine grain material would be partitioned using a triboelectric belt separator to collect the water ice particles from the regolith. Water ice concentrate could then be melted and neutralized, purified to remove any particles potentially implanted by the solar wind or other high-energy cosmic origins. The fine regolith particles could then be subjected to sintering via the powder metallurgy technique. Here, particles of iron, titanium, and aluminum could be partitioned out of the siliceous melt in their free metallic state and used for structural support. Thorium may also be partitioned out as well and used as a fuel in a meltdown-proof thorium reactor. The remaining siliceous regolith material could then be developed into a waterless, sulfur-based lunar concrete that may be used as a building material. This concrete would undergo further sintering to improve structural integrity and durability. Ultimately, this process may help establish a human presence on the moon by lowering infrastructure costs. This beneficiation technique can also be scaled down to meet the production capacity and needs of a fledgling lunar outpost. The envisioned processing system relies primarily on 3 separate technologies: high voltage electric pulse disaggregation, or EPD, triboelectric belt separation, EEBS, and powder metallurgy biosintering. EPD has the least amount of prior research in this processing system, but it has a huge potential. EPD is an alternative to the mechanical pressures used for comminution in the mining industry. Comminution is just our fancy word for breaking bigger rocks into smaller rocks, which expose more mineral surface area to assist in processing. EPD can achieve equivalent particle sizes of crushers and even finer, up to 5 to 10 picometers, with much greater precision. This technology utilizes a high voltage alternating electric pulse applied to a mineral sample. The pulse induces internal attractive and repulsive forces that put strain on the mineral's crystal structure, though it fails along natural crystallographic defects. This process continues as the mineral is progressively reduced to smaller particle sizes. The company Selfrag is currently applying this technology in industrial applications to improve recycling techniques, precision extraction for geochronological research, and conventional mineral processing plants. The current roadblock for this technology's mass adoption is energy inefficiency. However, due to low tonnage amounts from lunar surface mining, which would more likely better resemble an aggregate quarry as opposed to a full-scale metals mine, EPD's power and efficiency may be less economically debilitating and will only improve over time as modern electronics develop as well. TEBS arises as another alternative mineral processing technique, this time for the technique of flotation. Conventional flotation uses lots of water and other chemical compounds to liberate metal-bearing minerals from the waste rock, or gangue. Mineral particles stick to bubbles that float to the surface of a vat, where they condense into a mineral-rich foam, which is then scraped off. This means that contemporary flotation is heavily dependent on the Earth's gravity. TEBS removes the need of both water and the Earth's gravity from the mineral separation process entirely. It has done this by utilizing static electric charges on particle surfaces to separate particles of different charges using charged belts. TEBS also offers advantages beyond flotation, even in a terrestrial environment. Contemporary flotation has a hard time processing any particles smaller than 75 micrometers in size, while TEBS can work for particles under 1 micrometer and as large as 300. A 2014 study by Bittner, Flynn, and Herrock found when comparing TEBS and flotation on the same sample of the mineral barite, that the total operating cost TEBS was 75.8% total operating cost for flotation. This technology is currently being utilized in fly ash operations across the world.
Kerst, do you mind zooming in just a little bit?
Oh yeah, no worries. For the actual presentation, does that work?
Yeah, that's good.
Okay. The stumbling block for TEBS is energy efficiency the same as for EPD, but TEBS uses less energy than EPD and also benefits from a smaller tonnage load as well. Sintering is the most well-proven technology in this system and involves the heating of small mineral particles below their melting point until the outer edges of the individual crystals fuse together. This removes empty space in the crystal lattice and allows the structure to rework itself to create a stronger and more stable matrix. This technology has been used in the creation of ceramics for millennia and is currently a dominant formation tool for most plastics. In mining, this technique is sometimes referred to as powder metallurgy, which is fitting because the structural integrity of the reworked material is dependent on the size of the particles used. The smaller the particle size, the more effective sintering. The extremely fine particle sizes EPD can produce and TEBS can differentiate are large assets in producing the strongest possible lunar concrete derived from sintering. Regolith sintering already has a relatively extensive research base, including many real-world prototypes. The uniquity of this processing system is that individual elements of the lunar regolith may be partitioned out and utilized for different purposes in a lunar outpost. Small particles of free metallic aluminum, titanium, and especially iron can be found in the regolith due to the extremely reductive environment. The minerals tralite and apatite in the regolith both contain sulfur in various oxidation states, but mostly in its most reduced form, which is best for mineral processing. The element thorium can be found as a trace element in many minerals in the regolith in a reduced state as well. I may have to zoom out just a little bit, so can everybody see that though? At this section? Well, I'll just keep on going, and if anybody has any problems, just direct them to that. This section of the paper provides a research-based values for the in-situ resources that are available on and below the lunar surface, as well as data to help support the technologies laid out in the system to develop them. Surface water ice is most likely patchy on permanently shadowed crater floors, occupying approximately 11.5% of available surface. Ice may extend for up to 10 meters below the surface, which would indicate the existence of at least hundreds of millions of tons of water ice near the lunar poles. Approximately 100,000 tons of regolith could yield 150 to 200 tons of iron, with free metal comprising 0.1 to 0.5 weight% of the regolith. This metal could then be used to produce rebar, construction for concrete support, as 3D printer material for machine parts, or could be concentrated throughout concrete slabs to increase structural support and allow for magnetic transportation. Even comprising only 0.1% of regolith, material extracted from a 100 meter by 100 meter surface patch, thermally processed at 1100 degrees Celsius, could yield between 700 and 1,000 kilograms of sulfur. This sulfur could be used in the construction of sulfur-based waterless lunar concrete. This concrete could be instrumental in laying an infrastructure foundation for a lunar outpost. Thorium abundances for the South Polar region will most likely range between 1 to 4 micrograms per gram of regolith. It can be as high as 20 micrograms per gram in other lunar regions. While the least abundant regolith material mentioned, thorium could be utilized in a small-scale thorium-based nuclear fission reactor to provide power to a fledgling outpost. Unlike uranium-based power, thorium reactors are unable to fail by meltdown, cannot be developed into nuclear weapons. The figure from Lastra, Cabri, and Weiblin may be difficult to interpret at first glance, so allow me to simplify. The figure is from a paper comparing EPD to conventional pressure on the same platinum-bearing ore. The different colors in the bar graph, or in the pie graph, represent different minerals and their exposed surface areas, some minerals encased in less valuable rocks. This figure shows that EPD is able to comminute this sample much better than the crusher, with significantly more platinum-bearing minerals exposed. As you can see, the first image is the conventional crusher, and the light blue is unexposed mineral surface, while the red, yellow, green, purple in the second image are all exposed mineral surfaces. These figures add further detail to the TEBS process. The first figure shows the specifications for the machine itself with a feed capacity of 40 tons per hour. The second image shows how the charged belts are able to separate differently charged particles from an initially mixed state. This poster, at a minimum, should have led you to the conclusion that water ice, free metals, sulfur, and thorium may all be critical in-situ resources, establishing a sustainable and permanent human settlement near the southern pole of the moon. It would be fantastic, though, if, through this poster, we began to surmise that electric pulse disaggregation, triboelectric belt separation, and sintering of fine regolith material may help create lunar infrastructure such as building material, energy, and fuel. Thank you, everybody, for attending this presentation. And I will now open up the rest of this time for any questions you may have. I definitely didn't go the full length of time, so we have plenty of time for questions.
All right, please unmute yourself and ask any questions if you have one.
Kerst, this is a very basic question. You know, there are certain planetary bodies with complex geologic mechanisms will, you know, can concentrate ore, and we consider that to be a very valuable thing. Whereas on the moon, we have this gardening where everything's sort of tilled up, you know, and powderized. But it seems to me as though beneficiation that we do can sort of make up for the lack of ore bodies, and that we create our own ore bodies by concentrating the things that we're interested in. To what extent, like maybe from an energy standpoint, do you think that beneficiation makes, you know, the moon and Mars about equal in terms of its resources?
Well, I can't necessarily speak as much to Mars. I haven't done as much research on that. I do know that there are perchlorates in the Martian regolith, which kind of don't help doesn't help much of the process because of the high acidity, just toxicity that it brings. But for energy amounts, I guess, can you give a little more clarification to that question? I can actually over here, I have an approximate energy requirement for like the EPD process, which is around 43 it's electron volts. Yeah, kilo electron volts. Yeah.
Is that per a certain amount?
Yes. So basically, for the for that study, the EPD was operated for approximately 1 pulse per second for around 150 seconds at 43 keV, and due to that, 96.7% of the material passed through a sieve. And sieves are a very normal part of the mineral processing process to reduce particles.
Right. So from an energy standpoint, what I'm saying is that beneficiation takes energy, but if you're not having to raise to high temperatures or whatnot, I think these are fairly low energy processes that we're talking about here. And so, you know, like say, for example, if, I don't think this is the case, but if there was just, you know, iron or nickel iron bits spread out as though they're like pieces of sand and other pieces of sand, not really stuck together or fused together, but just imagine that was the case. If you were to run that over a magnetic separator, it would be great. I mean, you would have high concentration of iron, and that would not be much worse in terms of energy required to do that than if you were to find an ore body in which it was, you know, just a chunk of iron there. So to what extent, in your opinion, I mean, this is just a general statement, obviously the devil's in the details, but to what extent can beneficiation get around the lack of concentration on the moon of ore bodies?
Kind of how I see it, at least, is beneficiation isn't like an optional process for the development of any type of lunar resources. Beneficiation and all types of mineral processing are going to need to be a part of extracting any of these types of resources. And you're correct for iron, being able to use a magnetic separator, but for other types of resources, such as sulfur and thorium, particle sizes really just need to be reduced. And I would say that for comminution, like as you were kind of mentioning, most of the resources that are in the regolith are very spread out. I mean, they have, it's basically nothing like we see for ore bodies on Earth, because there are no collecting processes that we know of right now. But by by mining only, you know, the surface components of the regolith, and then being able to break those those regolith particles down to very small sizes, we might be able to better partition out elements of the regolith while potentially not being high energy. Like I believe that this has a benefit. This process may be potentially better than a process that melts the water ice out of the regolith, because with any type of heating element, you may lose a considerable amount of the water to sublimation, whereas this process could operate for the ice and the regolith at similar temperatures. And for the extraction technique, you wouldn't necessarily even have to differentiate between both of those resources. The EBS would hypothetically separate both very effectively.
Thank you.
I have a question. Does centrifugal force work the same way on the moon as on Earth? I mean, could we just take the regolith and put it into a container with water and then spin it and then get the different densities of material in different places?
I have been thinking about that idea, centrifugal operations, for approximately the last 4 or 5 years, because I've been thinking about this concept of mineral processing on the moon, because there's a very small research base. There's much more for teleoperations of autonomous robots and whatnot, but really not as much for the actual developmentation of resources using in-situ techniques. I believe, though, that this would potentially be better than a centrifuge, because with the centrifuge, especially if you don't reduce the particle sizes, it may not be able to as effectively separate, and because the water ice may be very similar to the regolith, and in various states may be encased by the regolith or maybe encased in the regolith, it may not effectively, because centrifugal force is able to separate things based on their density, and there may not be a significant enough density difference between the water ice and the regolith particles.
We actually have, oh, sorry. We have some questions in the chat. One from Philip. Have these techniques been tested in a vacuum environment?
Not at all. None of these techniques that I have mentioned have gone through any amount of testing. These are all conceptual as of now, but I do intend on performing some research. I actually would hopefully be able to make this my thesis work later on in my academic career.
There is a dirty vacuum machine in Korea, meaning that you can have dust inside the vacuum. So it's not my machine or anything like that. I just know it exists. I've been inside it. Not while it was on, but.
How big is that dirty vacuum machine?
Yeah, like I said, I was inside of it. It's like big enough for me to walk around in. It's probably 8 foot high and maybe 6 foot by 6 foot, something like that.
Yeah, I had the pleasure of being at the Plumbrook Station at NASA Glenn, the world's largest vacuum chamber. And I asked them if Congress provided the funding, would they ever allow us to turn that giant chamber into a dirty vacuum chamber? And he just looked at me, he just gave me a funny look and said, no, never, not in a million years.
Yeah, no. And so I think you specifically have to build a vacuum chamber with that concept in mind, that you're going to have dust in the chamber. Otherwise, you're basically screwing up all of your mechanism. You'd be ruining a perfectly good vacuum chamber. But apparently they've thought about this from the get-go, and that was the purpose, is to be able to do testing for materials on the moon.
Awesome. I'm not entirely sure what conversation you guys are referencing, but I know it's a good one. I haven't looked at the chat during this talk yet. Do we have any more questions potentially? From anybody else in the audience?
There's one from Chris. You kind of touched on this briefly, but he's asking about In terms of energy efficiency, are we better off taking raw regolith and crushing it to fine particles, or separating it by size and discarding the bigger pieces?
Well, see, that kind of goes into that question might be better explained with this graph too, with kind of the encasing, because if you have, like, if you don't start the comminution or the separation process with fine particles, you may lose some amount of the resources that you're trying to gain in those types of large rocks, because even though it may be encased in what appears to be gangue material, there could be, like in contemporary mining, this is kind of a normal thing that happens, that you have a mineral-rich deposit surrounded by gangue or in other ways associated by it. And so comminution is the best for exposing as much surface area as possible for these minerals, so that we are able to even detect if there are resources in that material. Does that kind of answer your question?
Wolf, does that, Chris, does that answer your question? Okay, it says more or less yes. All right, looks like we have some other one. What's the time? We've got 2 more minutes. Let's see, have, so Bill says, could you elaborate on how triboelectric separation works?
Oh yeah, absolutely. I kind of just showed an image of it, but I didn't really go further detail. Basically, how it works is it has 2 charge belts. There's 2 charge belts that move in opposite directions. And basically, and you can kind of see it has these little catches or something that would be inside the belt that would be able to kind of better control the regolith while it's in movement, so that it's not necessarily sliding all over. And because of the movement of the belts, you're able to generate a considerable amount of electric charge. And some particles would be attracted to the top of this belt section, whereas the others would be attracted to the bottom. And so basically, this entirely relies on a charge difference between the things that you would be. That's basically the of this machine. Kind of show the schematic maybe a little bit more.
We're actually at the end of the allocated time. But if you all have further questions, and Kerst, I'm not sure if we have Slack, so I encourage everyone to jump into Slack, and you can ask some more questions there. All right, thank you everyone, and I'll see you around.
Thank you everybody.